Can you see the screen now? Pradip?
Yes, yes, yes.
Okay. Okay. So let me welcome you to again to this class. So I will be trying to give you an overview on Verilog. So this essentially is would be the starting point of your like hardware design for FPGAs that you are planning to do in this lab. So without much ado, let me like start. So so the idea is that you have a design intent. So it could be very like anything for that matter. But let's start with a simple multiplexer. And suppose you want to implement this and you want to design this block. Okay, so we all know what the multiplexer is, I believe, from your switching class. So multiplexer is basically a logic element where I know that I've got say let's consider only 1 bit inputs. So there is like an input A and input B. Both of them are of 1 bit each, and there is a select line. So therefore, usually we try to make an abstraction like this. So we basically have this block or box, which is called as the multiplexer in this case, and it has got these signals like A and B in this case, which are received through input ports. So these are called as ports. Okay, so these are called as ports. Ports are essentially points through which your design block interacts with the external world. So it receives inputs. So there are certain, those ports are called as input ports. Okay, and likewise, there are some blocks which are called as output ports. So in this case, as you can see, there are three input ports, A, B, and select, and there is one output port shown as F. So the logic is very simple. I know that if the select is say 0, then I want this A signal to be selected and passed to the output F. If the logic value is 1, then I want that this signal is or B is selected and passed to the output F. So now I want to design this. Okay, so the question is, how do I design? That is one question. And the second thing is that where do I realize this? Because at the same time, I want to kind of like put it into some sort of chip, right? I want to realize this as a hardware unit. So in this class, we'll be trying to design this, like these kind of blocks using some kind of. So we'll try to develop a methodology for doing so, and eventually, right, try to prototype on certain hardware devices which are called as FPGAs. Okay, so these are like maybe this board or similar kind of boards you will be, like trying to prototype. I mean, since that is the whole objective, that at the end of the day, the design that we essentially have in our mind, or what we call as design intent, will be eventually realized on this block, which is called as FPGA. Okay, so this is what is the, so in this board you can see that we have just tried to highlight a specific block, which is essentially your target platform. Okay, so it is kind of an interesting platform because you are eventually getting a hardware, but at the same time, right, this hardware is actually a programmable hardware. Okay, so why it is programmable? Because today you suppose realize a multiplexer on this, tomorrow you can make it a processor also or something else. Okay, so you can essentially change and update your hardware, and that essentially is one of the reasons why FPGAs are so popular, because it essentially gives you kind of better performance in terms of, because of the fact that it is a hardware device, but at the same time you can essentially program and you can change your design. And that is why FPGAs have become more and more popular and are used nowadays in very exciting design projects. Okay, so just to kind of motivate you, this is a snapshot of an FPGA cluster being built in a Bitcoin miner at Princeton University. Okay, so like this, you can think of more fancy designs also. There are many applications that FPGAs can enable. So how do you design them? Right, that's the whole question. So finally, eventually we have an FPGA, and we would like to make our design, and we are at this point. So we have a thought, right, that okay, I want to design a multiplexer. So at this point, it is only a thought, right? How do I realize it as a concrete piece of hardware device? So the first starting point that we will try to kind of deal with at this point is are these first 2 points. Okay, that is essentially we will try to make a design of our, or no, describe our design by a specific kind of language which are called as HDLs. Okay, so HDL stands for hardware description language. Okay, so we will basically learn a specific type of hardware description language, as an example of this being Verilog, through which we will be able to describe our hardware. Okay, and once we have described our hardware, okay, so there are different ways of writing our hardware description, but once we have done that, we can feed it into our like software, which is essentially nothing but a CAD software, which does a lot of things actually internally. For example, what it does is that since your FPGA is a hardware device and it has got a like a fixed hardware resources, so maybe I mean I will very briefly talk about some of the internal components of FPGAs. And essentially what it does is it takes your design and it tries to map into those hardware components, okay, which are there in your inside your FPGA block. Okay, so it does a bunch of CAD operations. Like the first thing is what is called as this like high level logic synthesis. It basically tries to map it into an internal like AND gates and OR gates, which is called as netlist. So this is very popularly called as netlist, which is nothing but like, yeah, it's basically a connection of your AND gates and OR gates. Okay, and finally it basically does you really do not need to go in details here, but you basically do a certain sequence of steps which are called as mapping, placement, and routing, which essentially maps your Verilog description into the resources which are present inside the FPGA. Okay, the resources inside the FPGAs I will just briefly talk about in a few minutes, but at this point you can just keep in mind that these are some specific hardware resources which are there inside your FPGA device, and it maps it in a manner so that it essentially operates exactly as your design objective. Okay, but as you can understand that in FPGAs there are some fixed resources. Okay, so some of them you need to turn on and some of them you need to turn off. You have to program it, right? And in order to program it, your CAD tool comes up with this what is called as bit file or bit stream, which essentially turns on and turns off few switches inside your FPGA so that your FPGA starts to operate as your like whatever you want it to do. Okay, so in this case you want to realize a multiplexer, so eventually, right, some switches will be turned on and turned off so that your FPGA starts to work as a multiplexer. So that is essentially, so this flow is usually called as a design flow, okay, or digital design flow in our case, where we have got this original design idea and we are eventually trying to map it into an FPGA so that we essentially give it a hardware. So that is why the thing that you are writing right now will look like a software because you are writing a like a high level code, but what you are essentially getting eventually is a hardware device. Okay, so that essentially, so what we have to now learn is how do you write this like this code. Okay, so that is what we will try to study. Okay, so now let us try to take a little bit of very quick look into what is an FPGA, because it is good to know where or what is your design intent and where do you really want to like implement your design, right? So FPGA essentially stands for, it's programmable as I said, but it stands for, I mean its full form is field programmable gate arrays. Okay, so the idea here is that essentially it's a bunch of what is called as programmable logic arrays. Okay, so it's basically a programmable fabric, you can say, which essentially is like operated by electrical fields. Okay, so that is why it is called as FPGA or field programmable gate arrays. So it is basically nothing but a sea of logic cells which are connected by some routing channels. So I think maybe I'll just show you a diagram to like motivate this. So this is how an FPGA internally looks like actually. So the FPGAs will have some logic blocks and these logic blocks are as shown here in this part of the diagram. Okay, so this is a logic block. Okay, so this logic block essentially is nothing but like a fixed fabric which you can make it which you can make it operate like as a specific input output lookup. Okay, so that is why these are called as and since you can program them, they are called as configurable logic blocks, and they are connected, as you can see here, by a like an interesting connection of what is called as switch blocks and connection blocks. Okay, so these are individual CLB blocks. Okay, so the CLB blocks are essentially implemented here, and the objective of the CLB blocks is so that like it basically starts operating and functioning as a specific design. Okay, so if you want to get into inside the CLB blocks, so the CLB blocks are basically blocks which provides you with the computation logic. You will find that the CLB blocks are actually made out of certain units which are called as lookup tables or LUTs. Okay, so the lookup tables, these are very simplistic, like overview of what happens inside or components of the description of the CLBs. So inside it, there is a very fundamental structure which is called as lookup table. So therefore, you will find that when you see the resource counts, when you are mapping it on FPGAs, you will see that your tool essentially gives you some numbers like how many lookup tables are utilized in your design. Okay, so what are these lookup tables? So these lookup tables are essentially nothing but blocks which can be used to implement any fixed input function. Okay, so for example, in this diagram, I have shown you 4 input lines. So therefore, this lookup table can help you to realize any Boolean function which has got 4 inputs and 1 output. Okay, so how many Boolean functions can be there? You can see, you can understand that there are like 2 to the power of 2 to the power of 4 possible Boolean functions, right, which can be realized, and this block essentially can be programmed to basically like operate as any of these possible Boolean functions. Okay, now there are some peripheral logic also which are provided inside the CLB. So one of them is this carry chain block, which is essentially used to implement like your adder circuits. Suppose you want to implement an adder. Okay, and the carry chain is, as we know, a very important block. We'll see in the class in more details. Okay, in this course, how to design adders and so on. So there, if you want to make it, like if you want to enhance the performance, you need a dedicated carry path, which is also provided inside the FPGA fabric. Now this goes for more or less for the combinatorial part. Okay, so this is more or less the combinatorial part of your design. So this is the combinatorial part of the design, which means there is no memory as such, but you also need to like give supports for sequential elements, and that is provided by a specific block which is called as a D flip-flop. Okay, so this is something that probably you have studied in your switching circuit class, which is essentially a D flip-flop, and inside your CLB you also have those blocks. Okay, so together this kind of block is what is called as the CLB, or the configurable logic block, and it is present inside your FPGA. Okay, and these CLBs are interconnected. They are interconnected by like by certain very regular structures. So you have got these routing switches, which are essentially nothing but the switch blocks, and they are again these and there are rails, power like signal rails, like which are kind of arranged in a very regular fashion, and the CLBs are connected to these rails by some connection blocks. Okay, so when you essentially want to program, like, so we can understand that how they are connected and how the lookup table essentially works can be essentially denoted by turning on and turning off some switches. Okay, and those essentially are the the which switch should be like turned on and which switch should be turned off essentially can be indicated by some 0 1 signals, and that 0 1 signal is essentially what is called as the bit file. So once your CAD tool develops or generates this bit file, once you essentially take your bit file and you dump into this FPGA fabric, your FPGA essentially gets programmed or configured to work as a specific design. Okay, so this is on the very top level, like how an FPGA works, but of course, like we can get into more details as we get down the course. So now, I mean, we will not be really talking about this, but it is important to have an overall perspective of what you are basically doing this design. So right now we are basically bothered about this step where we are doing at the design entry. We are trying to kind of we have a design intent and we would like to describe it using a high level code, which is essentially, so there are many computing languages like VHDL and Verilog, but we will study in this course on this language is called as Verilog. And once we have this, right, we will take our CAT tool. So in this case, this Xilinx ISCA tool, which is essentially told to you. And once we have this code running in the program, essentially this works and eventually generates the bit file. And this bit file is passed through a specific cable to your FPGA, and your FPGA starts working as whatever you want. So eventually, right, we will see how we can, create such kind of designs from simple designs to more complex designs. Okay, eventually we want to implement a RISC processor which operates on the hardware. Okay, so that is the more or less objective. And after
Hello,
this,
sir.
right, hello, yeah.
Sir, my friend is not able to join, sir. He is waiting outside the meet.
Okay, so can some of the TS please help his friend to join?
What is his name?
Charan, sir.
I do not see any pending request. I already saw your message, but unfortunately I am not seeing any pending request.
Yeah, I saw your message, but there is nobody trying to join.
There is no pending request. So
So please ask your friend to send a request to join. We will of course definitely allow him. Okay.
Okay, sir.
Okay. So any questions till this point? Because after this we will get into the Verilog syntax and semantics of this language. So this is just to give you an overview on what we will be doing. Of course, we will be giving you tutorials on how to handle the tool and so on. But this is just to give you a very top level idea of what we are trying to do in this lab, and it's for the Verilog part. So any quick questions at this point? Hello. Hello.
No, sir.
Yeah, so please respond actually, because you see we are now in a situation where we are looking at the sky and teaching. Okay, so some responses from you will be very handy, like maybe yes, no, whatever actually. Okay, so does it make sense till this point? Some more inputs.
Yes, sir.
Okay, so can I ask one of you to quickly summarize what we are trying to do here? Anyone who would like to volunteer? Two marks bonus actually if you're volunteering. Anybody wants to say, like, summarize what we are saying here, what we are doing here?
We want to design hardware for solving a particular problem. So instead of directly going and assembling gates and ICs, we first model the problem, then we we describe it in a language that, in a hardware description language, in our case being Verilog, and then we use synthesis software like Xilinx that synthesizes that and writes, converts it into a form that an FPGA can understand, and it programs the FPGA, and then we have the circuit that we want to make without actually making the circuit.
Excellent. Thank you so much. Yeah, exactly. So that is what we wanted to tell this till this point. So now let us try to see inside a little bit into the Verilog design. So remember I told you about the multiplexer. So I will start from that point. Okay. So how do you write a multiplexer code in Verilog? Okay, I know that we are not acquainted with Verilog, but let's try to see whether we can, gradually understand the semantics and syntax of Verilog. So usually, the best way that I see of understanding how to write Verilog program is essentially, thinking of that in your mind, that you essentially have got, a specific design that you would like to make, and you essentially have got access to maybe some basic components, but you would like to kind of arrange those components together so that essentially, right, it tries to operate as a specific design. Okay, so maybe I would like to clarify what I said. So you know that when we normally talk about or making a, or classically, right, as you said that when you make a circuit, then you essentially do something which is on something which is called as a breadboard. Okay, so the breadboard is basically a very classic platform on which you put the blocks together and you connect them by wires. Okay, so that is the classic way of making a circuit. So for example, you may have some chips which work as AND gate. Okay, so maybe some chip which works as or an OR gate. Maybe there is an D flip flop, okay, or a flip flop, and certain other things, and you typically connect them by wires. Okay, so you probably have got, it looks pretty complicated, and eventually you have got a circuit. Okay, so right now we will try to do basically the same thing, but the only point is difference being that we will not be dealing with those hardware components, but we will try to describe them at a higher level. Okay, but in the form of a language. Okay, so these individual components which are there, which you are trying to assemble together, are essentially nothing but modules. Okay, and Verilog gives you an modular description or abstraction of your modules by using a specific construct which is shown here. So this is the, I would say, the starting point to understand how Verilog codes are written, is by these constructs or keywords which are called as module and end module. Okay, so any design that you have, okay, so you try to kind of always break it up into smaller parts and try to describe those modules in a separately in this manner. Okay, so let us start. In our case, we have very simple design to make, which is a multiplexer, and we fairly know the structure of how a multiplexer should be made by some basic logic gates. So this way of depicting a so we can write this or draw this or kind of describe the corresponding components which are there in a multiplexer. So one of them is shown here in this particular diagram. So you can see that this multiplexer, which is essentially the output of which is F, and as I said that so you would think, right, this is your something that you would like to design. So your inputs are A, B, and select, and the output is F. Okay, so you know that the output of F, right, can be obtained by A, B, and select by using these gates. So you have got an OR gate, you have got two AND gates and one NOT gate, so that when this select becomes equal to 1, then or maybe equal to 0, then this NOT gate gets inverts this logic. This becomes 1, and since you pass it into an AND gate, whatever is over here, this A essentially gets passed over here. On the other hand, since this is 0, this AND gate produces this output as 0. So therefore 0 or A essentially gets propagated to the output, right? So likewise, if I set it to 1, then B would get propagated to the output. So you see that you know two things about this multiplexer. So the first thing that you know about this multiplexer is its structure. Okay, you know its structure, and you also know its behavior, because you know essentially how a multiplexer behaves in terms of its inputs. Okay, now you know both, because this is a fairly simple structure, so you can write it in a very simple manner. So we'll start with this design. Okay, that is what is called as the structure, from the structure, and the code that essentially comes out from that is what is called as a structural way of writing the code. Okay, so how do you do that? And we'll always keep this breadboard paradigm in our mind. So what it basically is done over here is you have got this AND gates. So imagine that you have got here two AND gates. So think of in your mind that you take these two AND gates and you place them in your breadboard. You have got this OR gate, you place it on the breadboard. You have got this NOT gate, you place it onto the breadboard, and then you start connecting them by wires. Okay, so this is exactly what we will do here in the code as well. So the only thing is that this placement that I said on the breadboard is given a fancy name, which is called as instantiate. Okay, So this is called as instantiate, and this is what is called as the instantiation of these blocks. Okay, so what I do is I take this, so this, and in your Verilog you will see that there are already certain support for logic, and these are called as primitives. Okay, so these are essentially pre-designed logic which is already present inside the library of your programming language, or library support of your programming language, and these are called as primitives. Okay, so I take maybe the first AND gate, the second AND gate, and I just write them one after the other. So these are called as two instances of the AND gates. But you see that since both of them are AND gates, and I need some way of differentiating or distinguishing between the two AND gates, I give specific names to this AND gate. So I call, say, this AND gate as G1 and this AND gate as G2. So the syntax is as follows. So the syntax says, okay, if you want to kind of instantiate them, then you essentially, like write this AND gate, and you write the corresponding name of this AND gate. And likewise, right, for the second AND gate, you have got a name, say G2. Okay. So now the question is, right, what is an AND gate? So we know that inside, again, if you think about the module of AND gate, you know that there are two inputs, say A and B, and there is one output, which is, say, like Y. Okay. So therefore, right, there are two inputs and one output. So usually the syntax for an AND gate primitive is so what you can call is, you can write here AND G1, and there are three arguments, like two inputs and one output. So these are essentially shown over here, and the syntax is that the first one is the output and the other two are inputs. So this is the output, okay, and these two are the inputs. Okay, so there are two inputs and there is one output. So likewise for this AND gate also, there is there is one output and there are two inputs. Okay, so therefore, right, I mean, you can essentially write it in this manner. So you can write here AND G1, and the first thing that you will write here is essentially the corresponding corresponds to the output, and the remaining two ports corresponds to the inputs. Okay, so now remember I told you that, okay, you have placed the AND gates, but now you would like to connect them by wires. Okay, so you see, if you see this diagram now, you will see that I have given some specific names to these wires. For example, if I connect, say, like this AND gate's output port to the input port of this OR gate, I have given a specific name to this wire, and I call this as F1. Okay, and likewise, in this case, I have called it as F2. So likewise, each of the wires that I have essentially have been given some specific names. Okay, and there are, of course, like some input, like wires which comes directly from the input, and there are some which essentially goes directly to the output. Okay, so usually for these things, essentially, what we will be doing is, we will basically so in order to do this interconnection, we will be writing here these names and essentially writing them in the place of the AND gate is essentially connected to the input of this OR gate, and therefore I write here F1, which is essentially the name of this output wire. And if you see the OR gate instantiation, which is essentially done in a similar manner, and again, if the instance name is G3, then I write OR G3. So you can see that I have used the same name of the wire for the input, one of the inputs of this OR gate, and the output of this AND gate G1. So this means that this wire F1 is used to connect the output of this AND gate to the input of this OR gate. Okay, and likewise, you will see the similar thing for the AND gate G2 also. Okay, so in the case of AND gate G2, the output wire is F2. So I've given the name F2, which is used to connect to this input to this other input of the OR gate. So if you see the other input of the OR gate, it is F2, and that is used to connect it, correspondingly with this output of the AND gate G2. So that is why, like here I have written here F2, and here also I've written F2. The others are pretty straightforward, because like one of the inputs of AND gate is the input A itself, so I've written here A, and likewise, the other input of this AND gate is the input B. So the other thing that is also there is this inverter. So therefore, I've again instantiated or placed this NOT gate. So I've written NOT, and the name of this gate is not G4. So this is not G4. The input of this NOT gate is the select, and the output wire is called as N select, as you see over here. So that is why the first one is the output, as I said, by our by our syntax, and the second one is select. Okay, so that is the input. So you see that all these blocks are essentially placed, like in one by one, and essentially the idea here is that just like as in the breadboard, all these blocks are supposed to work together. So likewise, these blocks are also expected to work in a concurrent fashion. Okay, so the elegance of Verilog or Verilog kind of languages is that it essentially gives you a support for describing hardware. Okay, and one of the important requirements of such kind of languages is the support to model concurrency. Okay, so you need a a support to model this notion of hardware, that things in hardware actually operate concurrently or in parallel. Where what says if you have got maybe an imperative programming language like C, you will see that there is a top-down simulation, right? I mean, things go from the top, it gets executed, then you come to the next instruction, and so on. On the other hand, in Verilog, you need the support of concurrency, and that is one of the primary requirements for a language which supports or supports hardware description. Okay, so therefore this I will of course go in details into this, but this is just to give you a top level description of how these blocks can be placed together, and essentially they can be also interconnected. So now to complete this part of writing this modular description of the multiplexer, there are certain other important things that we also need to take a look at. So for example, when you write the multiplexer module, you first of all write this module, and then you give a name for your design. Okay, so that is the module mux. And then you give a port description. So port description would mean that what are essentially the individual ports of your multiplexer. Okay, so remember that I said that if you're in your multiplexer design, this is your mux, your inputs are A and B. So these are the input ports. The other input port is select, and the output is F. Okay, so therefore you write them in this manner, in this parenthesis, and the first one that you write is the output, followed by all the inputs like A, B, and select are essentially the corresponding inputs. Okay, and then you describe which are the output ports and which are the input ports. Okay, so therefore you write that okay, F is an output port, and for that you use this keyword called as output, and likewise A, B, and select are input ports, and therefore you use this keyword called input to describe that A, B, and select are input ports. And finally you write them or encapsulate them using this module and end module over here. Okay, so this is essentially gives you the the wrapper essentially, which is corresponding to your multiplexer design. And what you can do now is you can use this multiplexer module in some other files or other designs, and you can similarly use them or instantiate this multiplexer to work as a specific to operate as a required multiplexer. Okay, so this is like a very top level understanding about how you can design a multiplexer from primitives, because these primitives are essentially called as primitives, and so using this you can essentially realize the multiplexer. Okay, so now there are I have missed out purposefully, and I will go about tell or describe them gradually. But any quick questions at this point, I would be very happy to address.
Yes, sir, I have a doubt. Will not be the not G4 line at the top. It is not necessary that the not G4 line will be at the top, like before and.
Can you be little clear? I could not understand what you said.
So because like in the AND line we are using AND select as the input, but AND select is output is after the AND line, because not G4 line is after the AND line. So I am asking like the not G4 line. Okay.
No. So that is what I said. Like that. That is the beauty. You see, I mean, you essentially. You are essentially again thinking like in a C language, right? You are essentially expecting that a NOT gate will produce an N select and then it will be used in this AND gate. That is exactly what will not happen. Okay, because it is just like like the way you have to kind of think about this is exactly like, so in a breadboard, right? When you place your AND gates, suppose you use AND gates and you place your OR gate and then you have got your n select, right? Essentially, all these blocks are working together, are working parallel. Okay, so when the Verilog simulation happens, it also gives you a feeling of concurrency. Okay, although it is slightly tricky, but at this point, let's just keep in mind that we have this view of concurrency, which means it really doesn't matter in which order you place the AND gates, OR gates, and NOT gates. Okay.
And so there will be space before not and before not on after not. There will be space.
Yeah. So yeah. So those things of so that is more or less the syntax, right, of the language. And yeah, I agree what you are saying, that maybe I should have written a better blank over here. Okay. And likewise, you can see that I didn't talk about all these things, which I expect that will go and find it out yourself. That for example, this AND line ends with a semicolon and so on. Okay. And it is one thing that I want to again say, that this is not a function call. Okay, so like in C, we have function calls. It looks pretty similar, but it is not function calls, and rather we will not call them as function calls because there is something else. But rather we will call them as instantiations. Okay, and the main key point here is that all these AND gates, OR gates, and NOT gates are working in parallel, working concurrently. Okay, and that is essentially the key difference of how the Verilog simulation happens and what you will probably see in something like a programming language like C. Okay.
Yes, sir.
Any more question?
I
Okay.
got that you have that these are not function definitions.
Sorry.
Oh, that these module definitions aren't like function definition in C, C++.
No. So these are essentially what we will call as modules. Okay, so we will not call them as functions. In Verilog, there is something different, which is like the function calls in Verilog are slightly different, but rather we will call them as instances or instantiations. Okay.
Yeah, got it. So like while using these for example, in this example, while using this multiplexer, so I can call the multiplexer above the definition and below the definition, right? Or
yes. Once you have defined this multiplexer, you can now take these marks and place it in a bigger design. Actually, okay, you can instantiate in a bigger design.
Got it. Okay. Yes, sir.
Right. So now let's little bit make progress. So this is essentially the same thing. Okay, what we have seen so far, except that you see that I've added one additional line here, which is essentially this part. Okay, so here I've used this keyword. So in Verilog, right, like you have in any programming languages, there are also some data types which are very like distinct from something that you have seen in C. Okay, so there are two such important data types which I will talk about. The first one is the wire. Okay, again, so the idea here is that so the thumb rule here is that, I mean, which are not any identifier, which is not explicitly defined, we will default it to wire. Okay, for example, if you have got inputs like say A, B, and the output is F. Okay, A, B, select, and F. These are by default wires. Okay, but you see here that I have used some additional variables like F2 and N select, which are not defined to be anything. Okay, so therefore, right, for such kind of variables or identifiers, explicit data type, and the data type is in this type wire F1, F2, and N select. Okay, so once you write that, then you will see that you will not get, if you do not write this, you will get a syntax error. Okay, so you have to essentially explicitly write for these additional variables that you have written so you define this data type as wire. Okay, so there is another data type that is called as reg, and I will talk about that in a little while. So you can keep in mind that the first thing that essentially which you can do is any variables which you are using for interconnecting the blocks. Okay, so anything which you are using to interconnect the blocks, they are essentially you can think them to be wires. Okay, so you can define or declare those data types to be as wires. Okay, so is this point clear? Like, when will I write a wire data type?
So so in the previous module won't compile is what you said, right? Because we have not declared them as wires.
Yes, so you'll get a syntax error. So you have to, so it's the same code, just only I've added this F1, wire F1, F2, and select.
Okay. Fine. But then you also said that they default to wires. So
no, I said that the ones that already are defined like A, B, F, and select, they are essentially you don't need any explicit definition for them. They are they are implicitly wires, and actually they are 1-bit wires. Okay, so if you want to make it like more than that, then you need an explicit definition. But inbuilt or implicitly, right, they are treated as 1-bit wires. Okay, but you see that the lines F1, F2, and N select, they are neither input ports nor output ports. Okay, so for them you need an explicit definition.
okay, sir, got it. Thank you.
Okay, so I hope that this is clear. The other more little bit, the other way of essentially describing a multiplexer is shown here. So the one that I started with, right, essentially is with this knowledge of the internal structure, and so we call this coding style as structural coding style. The alternative way of coding is essentially what is called as behavioral coding, where I know the behavior of the design. Okay, so in this case, for instance, it's a multiplexer, and you know the behavior of the design. What is the behavior of the design? You know that, okay, if select is 1, if the select is 1, okay, so we know this logic that if the select is 1, then the output port F should be equal to B. Okay, but if it is 0, then F becomes equal to A. So you know this logic. So this is exactly the logic, right? Essentially, if the select is 1, then F equal to B, and else F equal to A. So this is something that probably you have seen in C as well. Okay, so you can write this behavior straight away, and your compiler should be able to understand that, except that in this case you have to use an extra construct which is called as this always block. Okay, so this always block essentially is another way of like describing anything inside your circuit. So this is essentially what is called as I will talk about that in a little bit. So this is essentially dedicatedly called, this is a procedural statement. Okay, so this is the procedure that you introduce explicitly for describing a computation block. The idea here is you can anything basically, like if you see here, so you see that this output F essentially depends upon certain inputs, right? Because it depends upon A, B, and it also depends upon select. Okay, so the idea here is that you explicitly write a procedure, and that is why it is called as procedural assignment, where essentially you can describe your behavior, describe the behavior of the design, and you encapsulate that by an always block. And inside that always block, you also write a specific thing which is called as a sensitivity list or a trigger list. Okay, so this is called as sensitivity list or trigger list. And inside that, so you see that there is this at the rate of sign, and inside this, and then there's a parenthesis. Inside this parenthesis, you write all those signals which are important to compute the output of this block. Okay, so for example, here the inputs are A, B, and select. So you kind of write them as A or B or select to indicate that whenever any of these inputs essentially change, that means A changes or B changes or select changes, then this block needs to be re-evaluated. Okay, so you need to re-evaluate this block. So this block needs to be re-evaluated. So the block is re-evaluated, re-evaluate the block. Okay, whenever any one of A or B or select changes, and this has the sensitivity list or the trigger list. Okay, so in your code you can actually have multiple always blocks also. So you can have like one always block, you can have another always block, you can have a series of always blocks. Again, always blocks gives you a support to model concurrency. Okay, which means that all these always blocks essentially are hardware blocks which are essentially working together. The idea being that whenever any of the inputs of these blocks to these blocks change, then this block is re-evaluated, and the output essentially is recomputed. So meanwhile, I mean, like suppose A, B, or select essentially has got a value and f is being evaluated. Until unless A, B, and select changes, then f or the variable or the output variable essentially holds the old value. Okay, and since it holds the old value, okay, so for such kind of variables, they have a specific data type which is called as reg. Okay, so here we write reg f to indicate that f essentially holds its old value. So I will like to make a cautionary note at this point to indicate that a reg has nothing to do with hardware register. Okay, it is actually, in one sense, very misleading to be tempted to think that a reg is a register and a wire is a wire. Okay, so here I will show. So I will show you examples where a reg need not be a register. Okay, so a reg is just a data type, just we have in any software programming language. So reg is just a data type to indicate those variables which needs to hold its old value. Okay, so the thumb rule is that if you have got an always block and inside that you write assignments, then whatever comes to the left hand side of your assignment essentially takes the data type of reg. Okay, so here in this case we have an always block. F is a variable which comes to the left hand side of these assignments. Then f essentially has to be defined or declared as with the data type of reg. Okay, so the corresponding hardware that you get over here essentially is exactly the same as that you will get in the previous description. Okay, so here this was a structural way of coding and this is a behavioral way of coding. Okay, so it essentially leads you to the same piece of hardware. So that is essentially which is told over here, that is a reg. So you have written a reg here. So the reg essentially is nothing but used to hold the variables which essentially are re-evaluated. So until unless A, B, or select essentially changes, then the value of f essentially remains as its old value. Okay, and for example, let's take an example. Suppose your select is 1 and your A is 1 and your B is 0. Okay, in that case, since select is 1, right, your B should be, so f should be equal to B. That means f is equal to 0. Okay, and suppose after some time units you essentially pass a different signal where you change this A or select to 0. Okay, so in that case what should happen is that this 0 should get updated to 1, and until and unless that happens, f essentially holds this old value. Okay, so such kind of variables essentially have been given this data type which is called as reg reg. Okay, so the thumb rule is that if you have got an always block, then and you have got some assignment statements, then whichever variables are coming on the left hand side of your equal to statement, you declare them as reg. Okay, so any question about when should you use a reg and this way of writing the code? The rest of the things remain the same. Okay, yeah, please go ahead.
I just had a small question. So a reg only has a utility when we are doing behavioral coding, right? When we are using an always block.
Right, exactly.
All right.
Yes. Okay.
So I have a question. Are both of these computationally same? Both of these writing styles computationally same or different?
They're exactly the same. So I mean, they will lead to the same hardware. Okay. Hello.
Yes, sir. Got it.
Okay. So there is a yet third style of writing the multiplexer. Okay. So which if it is fine, then I will go ahead, which is using a continuous assignment statement. Okay. So here you can write it very compactly using this assign statement. Okay, and using this ternary operator which you have seen also in C. So you know this logic, right? So I can write here select question mark B colon A, and this I can write just using an assign statement. So there is no always block, and the idea is that any change it occurs on the right hand side causes a re-evaluation, and f essentially gets its updated value. Okay, so in such kind of cases, remember, see that I am not using any always block. So right here, I do not write any explicit data type for, I do not need to declare f as reg. Okay, and if I do that, then I will get an error. Okay, so here it is not reg. So reg only comes when you are using an always block. Okay, so this is again, like a behavioral logic style of writing or describing the multiplexer, which essentially should give you the same piece of hardware. Okay, ideally it should be the same piece of hardware. So is this code also clear, like continuous assignment? So this is what is called as procedural assignment. Okay, so this is called as procedural assignment. Okay, and so procedural assignments are always encapsulated in this always block, and when you are writing using assign statements, then they are called as continuous assignments. Okay, so is this clear?
Yes, sir.
Yes, sir.
Okay, so now we are essentially, we are basically seeing, like 3 important logic styles. So maybe I'll just purely, go ahead and come back. So here is a quick summary of what we have seen so far. So we have talked about modules, we have talked about continuous assignments, and we have talked about procedural assignments. Okay, and essentially, right, it's I mean, our codes are essentially a combination of such kind of constructs. Okay, so let me give an example. So here, suppose I want to describe, like your weekend, and I describe that using a module. So I write here a module structure, module say holiday 1, and my inputs are Saturday, Sunday, and I want to determine whether it's a weekend or not. So the logic here, I can write them as a continuous assignment. So here I have described using the continuous assignment. So you say that in continuous assignments, I use the assign statement. So I write assign equal to weekend equal to Saturday or Sunday. That means if it is either a Saturday or Sunday, any one of them becomes 1, right? I know that it's a weekend, and that's the logic of your weekend. So the question that I would like to ask you is that if I suppose want to write this all using a procedural assignment, then what should be the corresponding code when I'm trying to express the weekend in a procedural assignment? Can anybody tell that?
So it will be always, first we have to make the weekend register reg, and
Okay.
then there will be always @sat or sun. If
So I will, okay,
Yeah,
okay, always at sat or sun, then
if sat equal to 1 or sun equal to 1, then
Right.
weekend is equal to 1.
Yeah, so I can write here weekend equal to sat or sun also actually inside this, right?
Yes, yes, yes.
Okay, so I have to define this as reg, and then I write here always at sat or sun, begin weekend equal to sat or sun. Okay, so exactly, so that is exactly what is written over here. So you can see that this is nothing but the procedural way of writing the or describing the weekend. Okay, so all of you are in page with me here, same page with me.
So just one question. You additionally wrote begin and end over here. So is that
Okay, so begin and end. I mean, if there are multiple lines, then I should write begin and end. Okay, so
all right?
yeah, I
All right.
just wrote that. Yeah, but it's
Thank you,
okay.
Yeah.
Okay, so now, I mean, some small details here which you can get from any standard textbook is how do you give names in Verilog. So usually, right, you give names which make sense, like to the signals, so that you later on when you see your program or code, you know like what they stand for. Few things that you which is told over here are, like that it can be any sequence of letter, digits, dollar signs, and all these things. So the first character must be a letter or underscore. It cannot be a dollar sign, and it cannot use characters such as hyphen, bracket, or hash in Verilog names. So just to tell you that there are some predefined syntaxes for the identifiers, and be careful about that. You may get errors because of choosing, like very, I mean, if some aberrations of these rules. Okay. So the other more important thing that I would like to stress here is this: we already seen the logic values like 0 and 1. there are two additional logic values in Verilog. Okay, so one of them is a cross and the other one is a Z. So cross stands for anything which is unknown or anything which is uninitialized. Okay, so for example, this is something that you can think of. Like for example, suppose you are describing an accumulator logic. So accumulator usually means that you have, say, an adder. Okay, so suppose you have an adder block and you have an input which comes to this adder. So this is the external input which comes over here, and there is a running sum which you are probably like maintaining in some kind of register and which is being fed back. Okay, so when you give an input, then the first input, for example, then this essentially, right, it needs to be cleared, right, because it needs to be kind of reset to some value. Otherwise the output of this becomes undefined. Okay, so in when you are describing or doing this in hardware, right, you need an explicit mechanism of initializing this or making this or resetting this sum to 0 value. So usually, right, if you think this as a register, okay, then you try to kind of have some specific signals which we called as reset, so that this sum register goes to 0. If you do not do it, right, then and if you do go ahead and do your computation, then you may get such kind of cross values when you simulate it. The cross values will mean that it's an unknown logic. Okay, so likewise, right, I mean, so you have to be very careful. Like when you see that crosses, right, then you know that there is some kind of such thing which is happening, because like unlike your programming language C, for example, I mean, you have to keep in mind that you need to explicitly write like some kind of hardware logic so that a specific register is initialized to 0. Okay, so that is one type of weird logic value that you need to deal, because in hardware such kind of things can happen. And the nice thing is that Verilog gives you that abstraction of such kind of logic values. When you simulate them, you should be able to know that there are like chances that you are ending up in making a design where such kind of unknown logics can crop up, and it is able to like capture such scenarios. And the other thing that is also important is the high impedance logic. Okay, and this can be by design also, or it can again be accidental. For example, it may happen that you have got two logic blocks and you essentially want to make a connection, but you forget on this connection. Okay, so this can go into a high impedance logic. On the other hand, right, there are certain things which are called as tri-state buffers. Okay, so the tri-state buffers are very popular actually. So the idea is that suppose you have got a block like where you are feeding in inputs, but you want to kind of give an input with a which passes through this tri-state logic. So the tri-state logic means that there is a specific enable signal, and if this enable signal is 1, then this input can say pass to the input to this block. Whereas if the input is enable is 0, then you want to block this input. Okay, the block this input means you just want to kind of like turn or make this switch open. Okay, so in Verilog, you essentially can model such kind of input lines also. And the usual way of doing that is like something very simple, like you have write it like if n, and suppose this output is a, so you can write here something like a equal to like 1 tick bz. Okay, so 1 tick basically means that 1 stands for the width, okay, and b stands for the radix, and z stands for the value. So this value is in this case a high impedance value. And this by the way, this 1 tick b, right, essentially you can do it for any signal. For example, if you want to just see this like this example of the multiplexer, if you wanted, for example, say a specific line a to be, say, like 2 bits, then you can do something like input 1:0 a. So that would imply that a is not 1-bit bus, but it is a 2-bit bus. Okay, so that is essentially standing for the logic of a. If you want to assign some specific value to a, then you can write something like this: assign a equal to, say, 2 tick b1. So 2 tick b1 would mean that 2 stands for the width again, and b will stand for the radix, and 1 stands for the value. So that means what you are saying is that a is assigned to the values of 0 and 1. Okay, so that is the usual way of like describing the values, multi-bit values in Verilog. So you can do like similar things even for the tri-state logic. Okay, so the other interesting scenario where such kind of crosses can crop up is like suppose you have got two hardware blocks, and you are like accidentally somehow like shorting them at some point. So it may happen that this logic block is trying to drive this high, and this logic block is trying to drive this 0, so that when the simulator sees this, right, it will not understand, and therefore will throw cross signals when it tries to simulate. Okay, so these are some additional logic values that Verilog supports, and they are very useful because these are certain logic values which can actually happen in real life circuit design. Okay, so are this idea of cross and Z understood, or any question on this cross and Z logic values? Hello.
So the values of cross and Z are defined, but like if I name a variable as x1 or z1, so that won't be considered, right?
I didn't understand. Can I repeat your question?
Yeah, like x and z are already defined in the Verilog, right?
Oh, x. Okay. By the way, it is not x. Okay, so it is basically cross. Okay.
Oh, God. Yes.
Yeah, and
So,
Z is essentially just to show you that there is a high impedance value. Yeah.
Yeah, got it. So, like if I define a variable like by mistake as z1 or something.
No, that you can do. Okay, so you can.
That won't pose a problem, right?
No, that won't pose a problem. Yeah. Okay.
Yes, you got it. Yes.
Okay. So I think yeah. So there are like this I've already described. So we can ignore the supply 1, supply 0. Okay. So fine. Okay. So by the way, I mean, just to kind of reiterate this point, since so this point, for example, so I will just to again reiterate this point that a reg data type, right, need not be a hardware register. So you see that this is an example of like these are two code snippets. In both of them, I have used this reg keyword. Okay. So in one case, so this is something that you have already seen. So I have written here reg C always at A or B. I have written C equal to A or B. So this is nothing but an OR gate, right? So this is an OR gate C whose inputs are A or B. So the C, right, is just a wire. It is not a register. Okay. Whereas if you have done something like this, right? So there is a specific keyword which essentially you can use in Verilog, which is called as posage. Okay. So posage would mean that you are trying to model a block for which so in this case, right, there is a specific port called as clock. So we call this as clock, and we are not only like triggering this at like when the clock changes, but we are triggering it at say the positive edge of the clock. Okay, so for such kind of constructs, right, essentially I mean, like of course, right, you are writing q equal to d, which means that the output is q and the input is d. So you are writing that whenever there is a positive edge of the clock, okay, then q becomes equal to d. So q is assigned d, the value of d. So this is nothing but a d flip flop, and in this case, right, this is an example where this q is basically a hardware register. Okay, so therefore in such kind of constructs, right, this is a hardware register, but this is nothing, it is a purely combinatorial block. Okay, so therefore having this keyword reg, right, essentially really has got nothing to do with whether it's a register or whether it's not a register, and therefore a reg keyword should not be confused with the register. Okay, so it becomes a hardware register only if you are using something like this. Then there's a like a instantiation that happens because of this, and because of this, right, it gets inferred into a flip-flop. Okay, so this is how you can model a D flip-flop. So suppose I ask you to like, or if you are interested to write a module for a D flip-flop, then this is the very simple logic that you can use to model a D flip-flop. Okay, so you may want some additional logic along with it actually, but like on the top level, right, this is as simple as that. So you can just describe your like write your Verilog code snippet in this manner to make this work as like a D flip-flop. Okay, so is this understood that like that the reg data type need not correspond to a hardware register? Okay, so please do not say register ever. Okay, when you are referring to reg is just a data type which is there in your Verilog programming like rule book. Okay, Okay, is this point clear?
Yes, sir.
Okay. Okay, so there's again a iteration on that point. Okay, so now I will try to talk about. So this is something that we have already seen. This with Redis. Okay, so yeah, so there's something also we have done. Okay, so now I think I will talk about a specific assignment which is there. Like in your codes. Okay, so we have been talking about, so in Verilog there are two types of assignments that you will be seeing. Okay, so one which I've already seen, which is essentially the symbol being this, and there is another type of assignment that you also see in Verilog, which is essentially denoted as this. Okay, so this one is an example of what is called as a blocking assignment, and this one is an example of what is called as non-blocking assignment. Okay, so I will try to take
Sir, you're muted.
hello.
Hello, sir.
Yeah, can you hear me now?
Yeah.
Yes.
Okay. Okay, so let me try to share once more. Yeah. So is my screen visible?
Yes, sir.
Okay. So I think I was not audible from this point. So I'll again start from this. So we are basically trying to distinguish between two specific types of assignments which Verilog uses. One of them is called as blocking and the other one is called as non-blocking. So this one you have already seen, right? This is called as blocking and the other one is called as non-blocking. Okay. So let's try to see that what is the distinction between them. So for instance, like blocking procedural assignments, the idea is that if you have got a bunch of blocking assignment statements, then like as the name suggests, blocking, right? That means that it will not allow the execution to pass to the subsequent statements until the previous assignment statement is executed. Okay. Whereas in a non-blocking procedural assignment statements, you can essentially like without blocking the subsequent statements, you allow the execution to be performed. So let me give you an example to illustrate this point. So the first one is a series of blocking statements. So A blocking 1, B blocking A, and C blocking B. Whereas the second code snippet is on A non-blocking 1, B non-blocking A, and C non-blocking B. So let us try to understand what is the difference when we execute both of them. Okay. So A equal to, so as the name suggests, blocking, which means that until and unless this one is executed, the next one cannot be executed. So therefore A becomes equal to 1, A gets assigned to 1, then B gets assigned to A. So B therefore takes the value of 1, and C takes the value of B, which is again 1. So at the end of the execution, right, A, B, and C, all of them essentially become 1. Now, if you think about the non-blocking scenarios, so in this case, since it is A non-blocking 1 and it doesn't block the execution of this one, so A becomes 1 like before, but B essentially takes the value or the old value of A before this assignment probably took place. Okay, so therefore B takes the old value of A and C takes the old value of B. Okay, so that essentially is the fundamental difference between having a blocking assignment, which essentially is the simple looking equal to, whereas in a non-blocking assignment you use this symbol less than equal to. Okay, where essentially and as you can understand, right, non-blocking assignment is also another feature that you have in Verilog to give support for concurrency. Okay, so is this example clear? Like, what is the difference between non-blocking assignment with blocking assignments?
So, sir, how would this look like on the hardware implementation?
Excellent question. Okay, so let's try to see. So exactly that is my next slide. So which talks about what is the hardware in the hardware, what is the difference between both of them. Okay, so in the first case, it is basically nothing but taking some buffers and connecting it one by one. Okay, so therefore you see that if I connect them one by one, then and I make the input 1, since these are buffers, all of them eventually becomes equal to 1. Okay, so basically this input 1 is nothing but you can think of this wire being connected to a high voltage, say VDD, and you are essentially driving these ports A, B, and C, all of them to 1. So eventually, right, everything gets the value of 1. Whereas in the non-blocking world or in the non-blocking scenario, you essentially have got something like a sequential element where the sequential elements are cascaded and connected with one another. So therefore, the idea being that whenever there is a positive edge of the clock, that means the clock goes to the higher edge, then essentially your assignments take place one by one. For example, what happens is C becomes equal to C. C basically takes, C essentially. So you can see here that I make this input as 1. So therefore, when there is a positive edge of the clock, then A takes the value of 1. Okay, whereas in the second register, element that you have here, when there is a positive edge of the clock, then B takes the value of the old value of A, because this is the old value of A, and that gets passed to B. So likewise, right, when there is a positive edge of the clock, C takes the old value of B. Okay, so therefore you see that this sequence of assignments is more convenient to model sequential circuit components, whereas this blocking assignments or these blocking assignments are more convenient for modeling combinatorial blocks. Okay, so does it answer your question?
Yes, sir.
Okay, so therefore, right, the thumb rule is that when you have got always blocks through which you are trying to describe combinatorial blocks, then use blocking statements. If you have got always blocks through which you want to describe sequential elements, use non-blocking statements. Okay, so here is a quick dry run to ensure that we all understand the difference between blocking and non-blocking assignments. By the way, in this code, you will see I've used this funny looking, like #3 and #1 and so on. So these are, certain things that I can use in Verilog to indicate delay elements. Okay, so these are nothing but I want to kind of indicate some kind of delay units, okay, or delay in my simulation. But these are not realizable in hardware. Okay, so these are essentially not. So if I just write, like a #3 or something like that, then the Verilog compiler essentially, or Verilog synthesizer, doesn't transfer them into some hardware components. Okay, so therefore these are technically what we call as non-synthesizable components. Okay, so non-synthesizable would mean that essentially, right, I mean, they have got they essentially have got you cannot synthesize this. Okay, so synthesis means like is a process of taking your code and converting them into hardware components, and if that is doable, then we call the code as synthesizable code. Whereas you may end up writing a Verilog program which is non-synthesizable, which means that by in simulation it will work, but if you want to convert them into hardware, then the mapping doesn't work properly. So then we say that these are non-synthesizable. Okay, so then the code is is not synthesizable. Okay, but see, in simulation it will work. Okay, so in this particular example, I am trying to illustrate you like how the simulation will work, and not really like trying to say that this is the synthesizable code. So let us try to see that like what will happen. So in this case, I've used a blocking assignment, and in the down part I've used a non-blocking assignment. So suppose the simulation starts at time t. Okay, so can you tell me like when assignments to M1 and Y1 will occur?
M1 will happen at t+3 and Y1 will happen at t+4.
Right. So M1 will occur at time t+3 and Y1 will occur at time t+4. Exactly. So what about the non-blocking scenario?
Sir, t+3 and t+1.
Right, exactly. So time t+3 and the down one will have at time t+1. So that means, right, you can see that yeah. So that is exactly what will happen here. Okay. So if you are using such statements, then you see that M1 is like assigned value at time t+3. So if this execution happens at time t+1, then basically M1, essentially the old values of M1 are being used. Okay, so this is basically a very simple example to illustrate to us the difference of blocking and non-blocking assignments. Okay. Okay.
Sir, I had a question.
Yeah.
So could you go to the previous slide?
This one?
No, sir. The one. Yeah, this one. So over here in the non-blocking part, when we are assigning A2 and B2 to M2, do we assign the new values of A2 and B2 to M2, right? Or is it the old ones?
You mean to say this
like
one?
the always block?
This one?
Yes, exactly. So,
yeah, so this one basically just means, so this is a trigger list, right? So it means
yes.
that this basically tries to model, essentially this basically tells us that whenever anything in this trigger list change, then this block is reevaluated.
Yes.
That's it. Nothing more than
Okay.
that, actually. Okay.
Okay.
Okay. Fine. So now, yeah. Sorry.
So can you just go back to that previous, just the same one you were on? Yes. Here in the trigger list we have M2, and we are also changing M2 in the block itself for the non-blocking part.
Yeah, so I think there is something fishy here. So I think there is a mistake actually. Thank you for pointing. So this will be C1 or M1 actually. Okay. So what I meant is anything on the right hand side of this basically. Okay. A2 or B2 or M1 or C1. Anything which changes essentially causes this block to reevaluate. Okay. Here it's same because it's A1, B1, M1, C1. So that's fine. But here there is a mistake. You're correct. Okay.
So even in the top one, there is M1 on the left hand side.
That is okay. I mean, it can be a feedback also. I mean, it can be a feedback. Okay, so that is not a problem actually. So the thing is, what you're saying is that A1, B1, M1, and C1, whenever anything of them changes, then this block is reevaluated. but it may happen that like that one of them. So in this case, right, it is just that that like if you think in terms of a corresponding logic, right, it means that A1 B1 are ANDed, and the output of that essentially is like is essentially your M1, and that is ORed with C1, right, with C1. Okay, and this block is re-evaluated. So this is your Y1. Okay, and what we are saying here is that anything A1, B1, or C1 changes, and then this block is re-evaluated. So I think you can remove out this OR M1. Actually, this is not required actually. So A1 or B1 or C1 changes. Okay.
Yes, sir.
Sir, I'll assign statements blocking or non-blocking?
Assign essentially. So when I said like blocking statements, I only refer to procedural statements. So these are like procedural statements, which means that they essentially make only sense when you have got always blocks. Okay.
Okay, sir.
So assign by definition is concurrent. Okay, so that means they are essentially working together. Okay, so there is no confusion about like whether they are blocking or whether they are non-blocking. So assign statements are essentially a mechanism of like having support for concurrency. So what I mean is that I may have like say assign. Just give you an example. F1 equal to say select question mark A or B. So maybe A1 B1. Okay, or and I may have like assign F2 equal to select question mark say A2 colon B2. So these are two multiplexers, right, which are essentially placed and concurrently executed. Okay.
Okay, sir.
So the confusion of whether something is blocking or non-blocking is only along with the when you have the always statement, because it is a procedural assignment. Okay.
See, DM, just if I just pitch in,
Yeah,
in
sure.
this example, in assign F2, I mean, suppose this is using F1 on the right hand side. Okay.
Yeah.
So then you try and understand, since you have a blocking call, both are equals, so that would make the second assign dependent on the first, right? So there will be a sequential execution. But
yeah.
But these are independent statements. So these are having parallelly. I mean, they will have a full concurrently. There is no dependency. If F1 is driving something which is a computation that is assigning F2, then there is sequential execution, and that sequentiality is forced by the blocking call. Okay, but in Verilog the convention is that in always blocks you have this this non-blocking calls, right? And in assign is more like what we call as data flow of computation. That you are on the right hand side, you expect a function, and its output and it's driving an output. Sorry for interrupting.
Yeah, so I mean, what I would like to say is that we simply put, right, again, whenever you are thinking about, like how the blocks are working, always fall back to your, like this breadboard style of design, because that would mean that, like if there is any dependency, you know that, okay, there is a multiplexer. Suppose I'm talking about a multiplexer logic, and this multiplexer logic is deciding what is happening in the next multiplexer logic. Okay, so the thing is that, like even in that scenario, right, essentially what you want in the hardware essentially is that I mean, it's not that like this logic essentially decides this logic and then this logic gets evaluated. Okay, because what you want is that all of these blocks, right, should work together, should work concurrently. And that is why you see that if you have got multiple always blocks, you can describe this using maybe an always statement and also this block as an always statement, and both of them essentially are working in parallel. So an equivalent way of representing them is using an assign statement. Okay, so essentially, right, I mean, the whole point is in Verilog you need the support for concurrency. That is essentially the main requirement of any hardware description language.
And so it is the combinational delays that decide like how much time you have to wait before the dependent one gets the
Exactly. So so when you do a Verilog simulation, they are all zero delay simulations. Okay, which means there is no gate delay inferred at this point. But later on, when you do synthesis, when you have done or gone more close to the hardware, then your tool can do something which is called as back annotation, which means like you can do simulation along with those gate delays. That is more realistic simulation. So that is why if you remember that design flow that I showed initially, you have to do simulations at different levels so that you are more realistic in your simulations. Okay.
Yes, sir.
Okay, so I think we are at this point where we can probably quickly talk about this other block. So I've been largely talking about writing the system model or describing the system model, but there is along with it another important component, which is in order to test your design. So that is called as a test bench. So writing the test bench in Verilog is itself I think probably 70% of the industrial job, but and it can be very complicated. You can do a lot of interesting things here, because remember that when you are writing the system model, you are bothered about writing synthesizable codes, but in test bench writings, you can be really go over the board. You can have fork, join, and many other interesting things of writing the test bench. But we will, for our course, we keep it simple. The whole objective is to basically give input stimulus to my system model so that I know whether they're working correctly or not. So therefore, what I do in the system model is I start giving this stimulus and I gather the responses, and I just have a result taker to know that whether it is working correctly or not. And together, both the system model and the test bench are run simultaneously, and we essentially see that whether my circuit is correctly operating. So I think when we see the actual tool, we'll see in more details about how to write the test bench. But here is a very top level description of probably how a test bench would look like. So you have got the multiplexer, as we have seen before. You can write it using continuous statements, you can write it using procedural statements, and many other ways, structural statements. But now I want to just give inputs to the multiplexer. Okay. So the usual way of writing the test bench essentially means that I have to basically suppose you have got this marks block here. So the marks block means it has got this A, B, and select, and essentially you have to pass these inputs. Okay. So the idea here is that the way that the simulation works is in this manner. So you basically write a test bench module. So this is suppose the test bench module. Okay. So this stands for the test bench, and inside this you essentially instantiate your system model. So this is your system model which you instantiate inside your test bench. Okay. So therefore, this comes and brings us to how do you instantiate blocks. Okay. And there are two ways in which you can instantiate blocks. Okay. So I just describe here both these ways. So suppose you have got a module which you have written as my module. Suppose the inputs are Y, A, and B. So the first one is called as connect by position. So this is a way of instantiating, as we have already seen in context to these primitives and or and not gates. So you just write my mod, which is the name of the module, and then write some name, unique identifier to your instantiation, and then declare Y1, A1, and B1. So in this case, Y1 stands in A1, B1 are all wires which are used to again connect these blocks. So likewise, you can also use another way, and this is something that I like more, which is called as connect by name. So in connect by name, so you essentially do not remember I told you that the first one is the output, the second one is an input, and so on. I have to remember that order. But when you are connecting by name, you don't need to do that. So what you can do rather is you essentially know that in your module, suppose your port is A, the input ports are A and B, and the output port is Y. So what you can do now is you can use this dot operator. So dot will stand for dot, and the dot A will stand for the name of the corresponding port, and the wire that you are using to connect to that port essentially is being told here as say dot A2. So that means A2 stands for the wire which is used to connect. Suppose you have a wire which you are using to connect to maybe another block here, and the name of this wire is say A2. Okay. Likewise, if you have got this port B and you are connecting it to maybe another wire over here, and you want to name this wire as B2, then you call this as dot BB2. And likewise, this output wire is say C2. So here in this case, you do not remember the order. So remember that I In this case, I have to remember like which one is an output and which one is an input, but here I can do it in this manner. Another advantage of doing or connecting by name is that you know the abstraction levels. Okay, so for example, you know that you know that this wire A2 and this port A are at different levels of the abstraction, which means that A2 is like a top level top level signal, whereas this A is essentially inside a module. Okay, so probably this is something that is, in my opinion, like more preferred, and when the design gets complicated, essentially it is better for debugging and like diagnosis of where things are going wrong. So now what you can therefore do is you can write your test bench for the multiplexer. So now let us see how the test bench for the multiplexer would look like. So again, you have got a similar construct like module and end module. Okay, and then you essentially have got your you need to, as I said, that in the test bench you need to instantiate your multiplexer. So this is the instantiation of the multiplexer, and you can see that this inputs as say the ports are say in 0, in 1, and maybe like the output port is out. So here and maybe the select port is a select. So what we do here is in the test bench you need to like trigger inputs for these ports for these ports, or the input ports of the multiplexer, which are shown here as input 0 and input 1 and maybe select port. So you do that using some dedicated wires. So therefore the wire names given here are S, A, and B, and the output wire is F. Okay, and note that here, I mean, like we have seen in always block, like we have seen this always block in describing the system models. In test bench, you have got something which is called as an initial block. Okay, so the idea is that whenever the simulation starts, this initial blocks comes into execution, and there you can essentially one by one like write down the corresponding signal value. For instance, you can write down that, for example, when the simulation starts, you can write A equal to 0, B equal to 1, and maybe S equal to 0. So these are the select lines, select values. And maybe after 10 simulation time, you can say, so this is the hash delay that I mentioned to indicate that after, so maybe this line is essentially done at say time t, and this particular assignment is done at time t plus 10. Okay, so what is the unit of this time? So often right here in Verilog we have something like, which I have not written here, is backtick time scale 1 nanosecond and maybe 1 picosecond or something like that you can write, which is essentially standing for the fact that this is the minimum time and this is the pitch of your time. Okay, so you can essentially define the unit of your time in this manner, and according to that you can provide stimuli to your system model. Okay, and likewise, right, what will happen is that the moment you are giving these inputs, when you are doing simulation, this block will result in output, and this output, right, you can match with, you can observe by using some special calls which are called as $monitor. There is something which is called as $display also, which you can see from any standard book. But what we typically prefer is to use what are called as waveform viewers. Okay, so you will see that inside your Xilinx IEC tool, there are some menus through which you can actually see the corresponding signal profiles. Like you can see the signals of your input ports, output ports, internal wires. Okay, and they are probably more useful for doing diagnosis for complicated designs. Okay, so that is usually like how you essentially provide stimulus to your input and you see the corresponding outputs. Okay, so any questions so far?
So this monitor statement will keep on
yeah, we'll
keep on printing at every time step, right? Not only after 10 second and 10 second.
No, this monitor will change whenever there is a change in the evaluation, right? Whenever there is a change in what essentially drives your block, there will be a re-evaluation, and that change will be displayed basically. Okay. Better to use a waveform viewer actually. That is more useful for doing diagnosis.
Okay, sir.
Okay. So, I mean, I think I was planning to, go in few more things, and one second. Yeah. So let's take an example. Yeah. Yeah. So suppose, right, I want to, design a very simple circuit where there is probably, I basically want to kind of implement a kind of circuit, right, which is just as an example, which probably comprises of this. Like suppose there is a counter, okay, so basically a simple up counter, okay, so and this counter essentially operates on some inputs, and there is a clock, okay, along with it. So as I said that suppose I want you to implement, say, like an accumulator circuit. Okay, what will it mean? It will mean that there is an input, and the input essentially gets incremented with your current sum, right? So a simple logic of that would be that, okay, I take this counter, which is basically a simple counter block, maybe an adder, and then there is an output register which you essentially which you can realize using a D flip flop, and the output of that is fed maybe to one of these inputs, okay, to the corresponding so what you can probably do is you essentially can so let's take an example. Suppose here you have got a mux logic, okay, so I'm just giving a hypothetical example. So you have got a mux logic and you have got an input here which you take from the user, from the external world, and then there is a select line here, okay. So the select line is initially set to maybe 0 or 1 depending upon how you connect them, and after that, right, depending upon the logic, you basically ensure that this feedback path becomes activated and this goes to your counter, okay. So it basically, suppose this is your design that you would like to implement, okay. So this is just a hypothetical example, but what I just try to kind of summarize what we have discussed so far with this very simple example, okay. So you see that this is the first thing that typically I would request you to look into, or we would try to encourage you to do it. So which is essentially the 0th level of your design. That means you essentially have a diagram, okay, which is your design intent. So never do a design without any diagram. That is the first thing. So I think we will probably try to say, sometimes randomly see that you have a diagram at your disposal, okay. The second thing is that once you have identified these blocks like this mux, counter, register, and so on, some of them may be easy, some of them will be not very easy, okay. So I mean really more complicated. So what you can do therefore is, for such kind of designs, what you can do is you essentially try to always develop a hierarchy of your design, which means that you have got a top level, okay, which is essentially always trying to make it structural, because here the kind of the structure which is essentially, suppose this, okay, and then you try to go into the internal modules, and you will see that some of these modules will be fairly simple, and if it is simple, then you can actually code them using behavioral style. You can just directly write its behavior and you can code them, whereas some of them will be more complex, okay. So therefore, if you see this module, maybe you need to further break it up into sub components, okay. And therefore, right, you will see that if you see this hierarchy, so maybe this is again a more complex block which you need to again break down. Maybe this is okay, and at this point you can make it behavioral, but maybe this block is more complicated and you need to break it down further, and so on. So your Verilog code essentially should not be like a one monolithic code where everything is together, but rather you should try to kind of have this kind of hierarchy in your design, okay, where when you go up, right, it will be more structural. When you go down, it will be more behavioral. So when you go to the leaf, right, it is more behavioral, whereas if you go to the root of this tree, or seemingly tree, right, essentially it is more structural. So for example, in this particular very simple example. You have got blocks like say mux, counter, and register. So what I would typically do is I will write a module for mux. Okay, so I will write say module mux, just like what we have done before. We will write this mux. Okay, I will write a separate. So I will call this file as say mux.v. Okay, and separate this. .v is the extension of the Verilog file. Likewise, I will write a file which is a module counter. Okay, and I will call this file as a module or like counter.v. Okay, counter.v. And likewise, I will write a module for this D flip-flop, and maybe I'll call this as module, like DFF, and write this down. Okay. So once I've written these modules, these three modules separately, my top level again will be just again interconnecting these blocks. So for example, what I will do is now I will write module, like whatever my accumulator or something like that. I will give my port descriptions here. So in the port descriptions here probably could be, if I give this as name as A, and this is a clock, okay, and then the output, maybe I take the output from here, so I can call this as a Y or something like that. So these are my port descriptions, right? So I write module and I write here an end module. So whereas these three blocks here, I will instantiate. So I will write mux, maybe M1. So I give a name here, say M1. I will again, like write an instance for the counter. So I will write say counter C1 or something like that, or maybe my module 2, whatever you want to do. So I can write here this is counter M2, and then I will write a D flip-flop or call it as M3. Okay, so this is my module M3. And now I will connect them. So for instance, I know that suppose this counter, in my particular counter description here, suppose I know that this counter essentially, like has got an output. Suppose this counter's output is denoted here. I can also see, remember, these are different levels of abstraction. So, like although this is a Y, I can also have this one as Y, and it doesn't matter. Okay. So what I will do therefore is I know that, okay, this is Y, and this register has got suppose an input, which is maybe, like say IN, and both of them are connected by this wire, and I will give a name to this wire. So suppose like the name of this wire is W1. So therefore what I will do now is when I'm instantiating here this counter module, I will have at some point like counter, maybe at some port, dot Y, and I will pass this wire name W1 to this. Okay, I will have some maybe previous and follow-up blocks as also, connections also. And likewise for this DFF, this port dot IN will have the wire W1. Okay, so that means basically I'm indicating this connection. Okay, that means the output of the counter is connected to the input of this register. Okay, so like this I will complete the remaining part of the connections. Okay, and for all these names like which I have newly introduced, I have to write here wire. Okay, so like wire W1 and so on. Okay, and of course I have to define the input ports, okay, and the output ports. Okay, so that essentially kind of completes my the top level of my code, top level of my design, and I have got my multiplexers, counters, and D flip-flops already written. And so I will take all these files, mux.v, counter.v, D flip-flop.v, and you will see later on I will build a project using the Xilinx ISE or something like that, and then simulate. Okay, so this essentially should be my usual way of developing the code. And if you are following this systematic approach, right, I can tell you that you can write codes very fast, accurately, and also you can diagnose your codes much easily, and you can explain to others also much easily. Moreover, if you want to do some kind of architectural maneuvering, like for example, if you're not happy with say a counter block, or you're not happy with the throughput, you can just change this counter by a better counter design, for example. Okay, you can probably introduce an extra register very easily inside here. So you can do a lot of maneuvering, which essentially will be possible if you do such kind of systematic code development. Okay, so any questions about this point? Hello.
No, sir.
Okay, so I think one final word before we complete this discussion. because this is also something that will come again and again. So we have been, so you'll see that your design is typically broken up into two parts. Okay, one will be a data path, and the other one will be a control path, which is usually made out of finite state machines. Okay, so in finite state machines, right? I mean, I believe that you have studied finite state machines in your switching class, right? Yes or no?
Yes,
Yes,
sir.
sir.
Yes.
Yeah. So typically you will see that any finite state machine, right, can be captured or illustrated by these three blocks. So one is basically what is called as the output logic block. Okay, and then there is a current state block, and there is a next state block. So the thing to note here is that the output logic and the next state logic are both combinatorial blocks. The current state logic is a sequential block. Okay, so this is a very simple model of FSM, and depending upon more details, it can be of variety of types, like what is called as mealy machine and mood machine. So the difference between mealy machine and mood machine, as we know, is that in mealy machine, the output logic also depends upon the input, which is not there in the mood logic. So in mood logic, there is output doesn't depend upon the input. So if you want, to code that, if you want to develop the Verilog program for that, the simple thumb rule is that have three blocks, three modules. Okay, so three modules, out of them, two of them will be combinatorial. Okay, so for example, you will have a next state block. So you see that I've just written always at control or current state. So this is a combinatorial block where I've got more interesting things which I leave to you as an exercise to look into, like the switch case statements. Okay, just like kind of C, what you do in C. So, but you can also use if else for that matter. But the main point is that this is a combinatorial block. Okay, so using this combinatorial block, you basically decide upon the next state. So the next state essentially gets decided because of this this block. Okay, so likewise, you also have an output logic block. Essentially, this is this block where, like in this case, it's a mood machine. So just the current state is telling me what is the corresponding output. I can also easily adapt it for a mealy machine. And then the third block essentially is your the current state block. So this is the only sequential block. So here you can use these constructs like positive of clock. So it's basically nothing but a D flip-flop. Okay, and the D flip-flop essentially means that the output of that is your current state. Okay, and the input of this is your next state, which you have got from the next state logic. And when the clock goes high, you just assign this, right? That is your logic. But in all your designs, in your good finite state machines, you should have a reset logic. Okay, that I already mentioned to you. Otherwise, you can get crosses and a lot of other things. So you need a reset. So there are two types of resets usually which are known. One is called as an asynchronous reset, and the other one is called as a synchronous reset. Okay, so this is an example of an asynchronous reset. So in asynchronous reset, in the code, you write a specific thing called OR positive of reset, which means that there is a reset line, and irrespective of what happens in the clock line, when there is a positive edge of the reset, then the output is zeroized or set to some state, a predefined state. So in this case, suppose that predefined state is ST0. So whenever there is a reset, that means the reset goes high, the current state is set to that initial state. Okay. Otherwise, whenever there is a positive edge of the clock, then the current state is assigned as the next state. So that is basically the logic of your current state block, and this is the only sequential element in your FSM. Okay, you can think of in that manner. So if you follow this, right, essentially you have a very clean design of the finite state machine broken up into three parts, and you will later on see, right, that this is exactly the same way in which you can code your control path of your processor. Okay. So this is a very simple example of an FSM. So suppose it's a car speed controller. There are four states like stop, slow, medium, and fast. So imagine that you are in a slow stop state and you accelerate, then you go to the slow state. If you accelerate further, then you go to the medium state. You accelerate further, you go to a fast state. The other way is if you are pressing a brake, then you go in the opposite direction. Otherwise, if you are not, you can write this logic like not accelerate and not brake, then it remains in the same states as it is. Now, suppose if I ask you to write a corresponding HDL code to describe this FSM, you simply break up into three blocks. Okay, so in this case there is no real output logic block, but there is a next state block and there is a current state logic. So if you see the code here, it is exactly that. Okay, so this block essentially is where the current state gets decided, which is a sequential block. So it uses posage of clock and all these things. Whereas the other part, right, is a purely combinatorial block. It just decides upon the next state in a combinatorial manner. So I use an always block, but this is not anything to do with the hardware register. Okay, so it is just, so of course, like you have to see more specifics, like but overall, right, this is the basic idea. So you have a very clean design of your finite state machine. Okay, so finally, right, I mean, so if you follow this, right, there are some comments, like you follow this architecture, you will see that you can FSMs, ALUs, and more complicated designs, as you will see gradually. You can essentially design using these techniques. So to conclude, right, I mean, write codes which can be translated to hardware, which is called as don't write non-synthesizable codes. Okay, and examples of non-synthesizable code that we have seen so far are the initial blocks that we have used in test benches, which are used to set up the initial test stimuli. These do not have any obvious hardware component. Likewise, the delays like the #5 and #3, they may be in Verilog source, and simulation wise it is okay, but the synthesizer will just ignore them. So in short, write codes with the hardware in your mind, okay, and do not depend upon the tool to decide upon the resultant hardware. So think about the hardware and then write the software. That's the whole message. Okay, finally remember that you are always a better designer than the tool. So don't like blindly depend upon the tool, because that essentially will not be very productive. Okay. So thank you. I mean, we'll see more nuances and more details down the line in the class. And if there are any questions, I mean, I'm sure there are many questions. But what I would request you is to go back and try to get hold of some kind of simulator, start getting hands-on actually. So because any programming language, that whether it's software or HDL or whatever, right, you need to write codes to understand how to do that. What I wanted to give you is an overall thing, at least a flavor of the syntax and more importantly, the semantics of code. Okay. So, right, what is the difference between syntax and semantics? Anybody?
What syntax defines the grammar, while semantics ascribes meaning to what is obtained after using the grammar rules.
Yeah. So simply, an example is that suppose I tell you that there is a cow which is dancing on the tree. It is syntactically correct, but not semantically. Right. So therefore, right, I think the whole message is that we should write Verilog codes which looks like hardware, okay, and not like mere replicas of C programs, because that essentially will not be, be really productive and not efficient, even if it works correctly, actually. Okay, so, and I mean, the whole point why we are studying HDL here is not just to write a program, right? Because that you can anywhere write in C. What we are trying to see is whether you can describe a hardware. Okay, so therefore, it will also be fun actually if you are able to depict the hardware at the beginning by a nice diagram, and then you go ahead and write the corresponding HDL code for that. Okay.
Sir, how do we set up Xilinx? I mean, Professor Chakraborty sent us a link, but then like the installer has several weird options and
so
yes, sir, it would be great. It would be a great help if you can like demonstrate like how to install and like run a
or
simple
what to
code.
install.
Sure. So we'll work out that actually. So I think yeah. So
one thing can we do, like we can ask, let's say, Pradeep and Primangshu to make a video and post here in the Teams.
Yeah, that would be very handy. So maybe we can, Pradeep, are you there, Pradeep?
Yes, sir. Yes.
Yes. So maybe this is something that we can work out actually. Okay. So like, then it would be very handy if you can make a video of an installation process, right? And just share it with the students.
Okay, sir.
You can, can take one of the systems where there is no Xilinx, right? And while I mean you do the install process, and while doing the install you speak about what are the steps you are taking, and while all this is happening, have it get recorded inside Teams and then post the video.
Okay,
So
okay,
maybe give us the link of the video, we can post in Teams.
okay, sir.
Okay. So any more concerns? Of course, like this is something that we will solve. Okay, so that will be eventually sorted out. Any other comment? So meanwhile, actually, you can even write your programs in iVerilog, but the only thing which I will request you is to write your codes in this modular fashion that we discussed. Actually, you just don't write your codes which are probably available in some resources and so on, but try to see that whether you can write them in this modular fashion. But I think we'll fix the Xilinx ISE quite soon, so it should be okay. Okay. Any more questions? Any more concern? Yeah.
Sir, I was not accepted. I mean, my request was not accepted for this Teams computer organization. I accepted.